For our next speaker, we'd like to welcome John Troeltzsch back up to the stage. John has 30 years history working with Ball Aerospace. He's currently the project manager for the Kepler mission for Ball Aerospace and has also worked on the Spitzer Space Telescope instrumentation on the Hubble Space Telescope. And although he won't be describing how to launch LSST into space, I think he will be talking about how to launch other telescopes into space. Please welcome John Troeltzsch.
Thanks, Ryan. So I'm here to talk about my tiny little telescope after that enormous telescope. And I'm also going to show you my new virtual clicker right here. When I point at the screen, he's going to change the slides for me. So I'm here to share with you a story about how humanity has positioned our generation to solve a very important problem. And you've heard lots of speakers today explain the asteroid problem and what a threat it is. Well, that's me going back one slide. Well, I'm going to share with you how we can use the last 60 years of scientific achievement to really solve this problem. And by solve it, I mean solve it, not study it, not try and solve it, but solve it. So although the Earth seems timeless, right? You look outside today, it looks about like it did yesterday. The land that I live near looks the same as it did when I was a kid, more or less. The cliffs in California tend to slough off in the ocean, but in general, our planet appears pretty much the same as it has generation after generation. Although the Earth is positioned in a very large, very dynamic environment called our solar system. Sometime between 2010 and 2012, we actually have a satellite around Mars that could take pictures and determine that a crater showed up. This crater is 30 meters wide, and an ejecta from that crater flew as far as 15 kilometers away from it. Now, the physics of crater formation and asteroid impacts on Mars are very different from the Earth. But here's an example where just in the past few years, a large rock has hit a planet in our solar system. So this stuff does happen. So if you wanted to predict an impact like this and then prevent it, how would you go about that? Well, the very large ground-based telescopes look in the visible light, same light that we use our eyes to see in. But there's another way to look for asteroids. The sun's atmosphere is at about 5,300 degrees K, and the energy is emitted in these visible wavelengths that telescopes like LSST can see. Now, this can also warm an asteroid in space. So just like if you put a rock out in the sun on a cold day, it'll warm up. Asteroids warm up when they get close to the sun. And once they warm up, that heat is distributed evenly around the asteroid, and then they re-emit the light in 7 to 14 microns. That's the infrared. So if you had night vision goggles, you'd be able to see this. So how would you go about asteroid hunting from space? Well, first you need a telescope that's sensitive to this asteroid's heat. Then you need to be able to detect and isolate the motion of the asteroid. So you're going to have to position the telescope to be able to stare very precisely without moving or wobbling. You need to locate it away from the Earth's interference. Although LSST will find a lot of asteroids, they have night to deal with, daytime to deal with every day. If you're out in space, you really get 24 hours a day to look for asteroids. The other thing is if you get far away from the Earth, you don't have the Earth in your field of view blocking part of the sky. So if you go to deep space, you get a good uninterrupted view of the solar system. Finally, you need to be able to communicate your findings to Earth. Well, so how do you do that? Well, first you need a camera, right? And in the 1990s, we had these fantastic infrared arrays that had 65,000 infrared pixels. That's 0.1 megapixels. Wow. Could not do an asteroid hunt with a detector that small. Now, moving ahead a little bit, we invented the Kepler camera. Now, this is a 95 million visible pixel camera, so it's a 95 megapixel camera, but it works in the visible light. And to give you some perspective, that's a $38 million camera that would fit in about 1.5 cubic feet. So space is not necessarily cheap, but this is the camera that was used to find over 1,000 planets around other stars in our galaxy. So we need to take that technology and this concept of putting detectors together to make a compound camera. And if you do that, you can put together a camera that looks like the one that we're thinking about or planning for Sentinel. This is a 28 million pixel infrared camera. So same concept, you put a bunch of detectors together so you can cover a larger portion of the sky. So now we can run the video. I'll give one more shot and then I'll narrate it. All right, so let's go back. No, yeah, go ahead and show the video. Roll the video. So here you can see light going through an infrared telescope and onto the infrared camera in the back. Here's a schematic of Sentinel out in space looking for asteroids. And what you're going to see now, that's a black background, and there's an asteroid or a piece of meteorite that was sitting against the black background. It's almost impossible to see it when it's sitting there against the black background. But now when I take an infrared camera and hold it up in front, it just pops right out. So that's the beauty of this infrared camera for looking for these very small, very dark asteroids in space. So one interesting thing about these cameras is they have to be kept very cold. They have to be kept just a few degrees, for example, 45 degrees above absolute zero. Now the way we've done that in the past is with great big tanks full of very, very cold fluid, liquid helium in the case of Spitzer. Now this tank weighed 660 pounds. It was launched with Spitzer in 2004, and it had a 5.5-year lifetime. Well, the way Sentinel will cool its detectors is using a refrigerator that only weighs 40 pounds and can last 8.5 years. So just in the course of 10 years, we've moved from requiring big, heavy tanks of coolant to being able to use these mechanical refrigerators to cool the camera. Now, this is the same kind of refrigerator that's being used on the new Landsat mission that Ball helped launch a couple years ago. So these coolers are up in space today, helping take those pictures of the Earth that you see from Landsat. So you can imagine a patch of the sky with, let's say, 3 asteroids going across it, and you can imagine moving your camera across it. Well, the key to finding the asteroids is that they move and the stars behind them don't. So if you take a picture and take another picture an hour later and look for what moved, you can sort out the things that are likely to be asteroids. Now, if you come back 2 days later and do that process again, now you can start to connect those dots. And if you come back 26 and 28 days later, you now have enough information that you can put that orbit together that you just heard about. So it's the same basic concept. You look for something that moves, and then you connect the dots in a very logical way using Kepler's laws to figure out what the orbits are of your asteroids. So one interesting thing about space is it's very big, and a satellite like Sentinel gets a long ways away. Sometimes it's actually going to be on the other side of the sun. So the distance between the Earth and the Sun is about 93 million miles. So you can imagine needing to communicate with your spacecraft over millions and millions of miles. How do you do that? Well, on the satellite side, you use an antenna very much like the Kepler antenna shown here, on the order of about the height of me, maybe a little taller. You put that on the spacecraft, and you hook it up to about a 35-watt radio, right? 35 watts, that's about equivalent to our modern fluorescent bulbs. In the old days, you'd say that was a fraction of an incandescent bulb. But the secret is you put a huge antenna on the Earth. So NASA's built a deep space network that has 3 of these 70-meter antennas. One's in California, one's in Australia, one's in Spain. And as the Earth rotates, these are pointing into various, out into space. And if your satellite's in the field of view, you can communicate with it. So using the 1-meter antenna and the 70-meter antenna, you can move about 4 megabits across 50 million miles. Now, that's not a very good internet download speed, but for the kind of distances we're talking about, that is sufficient to get the data down of those asteroids that we have, or those targets that we've got that have moved. So there are lots of places to look for near-Earth asteroids. You could look from the Earth, you could look from Chile, you could look from low Earth orbit, in which case you're going around the Earth and have the Earth in your way a lot of times, like Hubble does. You could go out by the moon and look from there, or you could go into an orbit down around Venus. Sentinel would use the Venus orbit, but the key is to get out where the action is. And you can see here all the different asteroids, and if you get into an orbit down around Venus, you're going faster than the Earth's orbit, so you're effectively lapping the Earth, and that allows you to really sweep out a large amount of space looking for these asteroids. So a space telescope gives you a very clear view. There's no air, there's no disturbances. It's very cold, so that infrared camera I was talking about has to be kept cold, and the refrigerator helps do that. But we can also use the coldness of space to help dissipate heat. So a combination of what we call passive cooling and active cooling gets it cold. And we need to be very stable. If you think about a spacecraft, there's not a lot of disturbances. You know, the ground's not shaking, the wind's not blowing. It's a very stable environment. So in the beginning, which really was just 60 years ago, these are pictures from Ball Aerospace. Here's the first folks that helped form our company out in the parking lot working on a satellite, okay? Here's a picture of that satellite. You can see how big it is and how they're working on it. Very, very simple machines. You know, these were the very first satellites that were launched by our country, by the world for that matter, some of the very first. So this is kind of where we set the stage at the beginning. Today, we've accomplished amazing things. We've built the Spitzer IR Observatory. I worked on Spitzer for years. This was able to see organic hydrocarbons in another galaxy, right? So imagine that. We're seeing diesel soot in a galaxy that's not our own. So very, very powerful astronomy, just incredible. And the camera on that telescope ran at 1.5 degrees above absolute zero. So incredible cold telescope. Here's Kepler. Kepler's managed to find over 1,000 planets. Sorry, I pointed at the screen, but I didn't mean to. Kepler's managed to find over 1,000 planets. So in the past, if the Earth got hit by an asteroid, you could just chalk it up to bad luck. You know, there was nothing we could do about it. But today, using these technologies, this infrared technology, the deep space technology, we're able to make the impossible possible. So imagine our ancestors watching Tunguska happen, right? Big asteroid comes in, hits the Earth. They would have been terrified. They would have been helpless. But today, we can build on generation after generation of knowledge to really solve a problem. We're at a point in history where we can solve a problem that has global impact. It's a threat that comes from off of our planet. So we live in a world where we could make this asteroid problem go away. We have the technology, we have the knowledge, we understand the plan. So with that, I'm going to show you a new game we've invented. Everybody here has played paper, rock, scissors, right? Well, now we're going to play asteroids, humans, dinosaurs. So dinosaurs beat humans. At least that's the story. Humans will beat the asteroids if we get our act together. And asteroids beat the dinosaurs, right? So everybody ready? So this is humans, okay? This is dinosaurs, this is asteroids. So on the count of three, everybody goes and look at what your neighbor does. 1, 2, 3. So now you've got it. You know how to play asteroids, humans, dinosaurs, and let's hope the humans win. Thank you.